Good morning, good afternoon, everyone. We appreciate your time and effort for joining this webinar today. We will talk about expanding infrastructure and data protection further down to the edge, a combination of confidential computing and crypto services to expand the infrastructure security and data protections in your edge solutions. In a prosaic way, edge is everything that is outside the data centers. It means almost everything from a tiny little device up to the international space stations, where you can find large servers operating significant IT operations. So intuitively, the protection of this element from IT attacks should adapt to the nature of these nodes. We cannot blindly apply a solution to this heterogeneous environment that is the edge, but we cannot force the business to adapt to each edge node. It will be too cumbersome and counterproductive. How can we protect data and workloads up to the edge in a simple and transparent way for the business? We will try to provide our answers to this question in this webinar. With me today, I'm very pleased and honored to have Mathieu Legray, Vice President Product at SciSec. He will explain how SciSec leverage confidential computing in addition to other security measures to deliver a secured, distributed architectures from the core to the edge. And myself, Luca Gabella, I'm responsible for the edge computing business in SciSec. This webinar will be a dialogue between Mathieu and I around the security challenge you may face in edge computing solutions and the security solutions that SciSec proposed based on real example we are facing daily. Briefly about SciSec. It's a bit more than 4 years old European company. We are based in Switzerland, and we have today a subsidiary in France. We are a bit more than 30 people, mainly engineers, working in SciSec. The SciSec missions, in a short, is to shorten the time to market of innovative, sensitive, and mission-critical business logic solutions. We do this by facilitating their integration into a trusted IT environment where company can protect their critical data and in all time, everywhere along the different architecture they are leveraging. Before moving forward, just to let's do some housekeeping. During the webinar, you can add your question in the chat, or at least there is a layers you see usually on the right side where it's written questions. Please add your question there, and we'll be more than happy at the end of the webinar within the Q&A during the Q&A sessions to answer these questions. So in the title of our webinar, we talk about a combination of confidential computing and crypto services, expanding the infrastructure security up to the edge. Before moving forward, I believe it would be good to define some of the terms we will use in today's webinars. So Mathieu, could you explain us a little bit and to the audience what means confidential computing and what challenge, problem it intends to solve?
Yes, of course, Luca. So in a nutshell, confidential computing is a technology exploiting hardware-based trusted execution environment to protect data while in use. This description is quite dense and might not be straightforward for people who are not familiar with this technology. So let's step back and consider the traditional cryptographic means that are used to protect data. So first, while data is at rest, this means stored in a persistent memory like a hard disk. It is pretty common to encrypt this data to protect its confidentiality. Second, while data is in transit, this means transmitted between two remote entities, the use of authenticated and encrypted communication channels is well established. So data at rest and data in transit are the data states that are currently protected in most cases. Confidential computing is a technology that protects data in use, another type of data states. Data in use means data while it is processed. This type of protection might be needed when you are running your business on a third-party infrastructure. This third party has the privileges or the capacity to dump volatile memory such as RAM memory. These privileges or capacities might be based on digital or physical accesses. The typical example is business running in public or hosted private clouds. Let me remind you that in cloud environments, your business processes are executed in the same processing units as host processes. In this case, you might want to ensure that your third-party host cannot access your business data in the RAM memory or in registered of your processing unit. Confidential computing provides you an isolation of your business processes and data from the host processes in processors to prevent this kind of new threats. So Luca, these are the main aspects that our audience needs to know about confidential computing for the rest of the webinar. Let's continue with the next slide.
Yeah, so in the next slide, basically, CySec leverage confidential computing and other security components to deliver its own solutions. Its engineering team has developed many elements to enrich its offering. I don't want to go through an extended marketing message, but Matthew, you are Vice President Product. It will be good if you can explain in synthesis what is the core offering of CySec today, and what that allow it to claim, to protect data and workload from the data centers to the cloud up to the edge at all times.
Okay, sure, Luca. So CySec solution is called ARCA Trusted OS. It is a Linux-based micro-distribution designed to run containerized applications. So one important differentiator of our solution is security. However, let's start with the container management capabilities of ARCA. ARCA allows the management of containers through a standard Kubernetes orchestrator. We can see the ARCA layered model in the figure on the left of this slide. On the bottom, there are some secure elements, hardware elements. I will explain a bit later how they are used. Above these hardware elements, this is where there is the OS. The Kubernetes orchestrators lies on this OS. And then on the top of this orchestrator, we can see the containerized application of the end users represented by these blue balls. So let's come back now to security. In terms of security functionalities, ARCA has been designed to address two types of threats. First, system intrusion from a corrupted application or an unauthorized access to the hardware. And second, business data theft or corruption while data is stored, transmitted, or processed within a cluster of ARCA execution environment. So to contain system intrusion, our operating system follows most of the recommendations given by NIST in their security guide for containerized applications. SP 800-190 is the name of this NIST special publication. So first, ARCA is what NIST calls a container-specific OS. This means that only containers can be executed on ARCA. This is done to reduce as much as possible attack surface on the host OS. Second, ARCA Trusted OS is an immutable operating system to strongly limit the possibilities of modifications of the host OS from containers by end users or malicious parties. And then the last part, a chain of trust or secure boot is executed at each boot of ARCA, and it is based on hardware elements such as TPM. We do this to ensure that ARCA Trusted OS is indeed a trusted execution environment. Then to prevent data theft and corruption, ARCA provides several security mechanisms. First, a full disk encryption is used by default to protect ARCA and the containers deployed on it, while the data is at rest. Okay. ARCA second, so ARCA leverages confidential computing to protect data while in use. And then finally, some Kubernetes curated components are proposed to secure network communication between the nodes and the pods deployed on ARCA Trusted OS. And then, in addition to all those security measures mentioned previously, which are used to secure the clusters of applications on ARCA, ARCA embeds also a cryptographic API that can be used by containers to either securely communicate with entities that are outside the ARCA cluster or to perform some cryptographic functions for business purposes. Okay, so Luca, I've described what confidential computing is and what are the main features of ARCA Trusted OS. You told us that the edge is everything that is outside the data center. Could you please explain this a bit more in details and why you have said there is no one fit for all security solution for the edge?
Let me start with a definition. It's a definition you can find in Wikipedia. Edge computing is a distributed computing paradigm that brings computation and data storage closer to the source of data. This is expected to improve the response time and save bandwidth, and also to respect some constraint in the physical world on one thing. It is an architecture rather than a specific technology. It is a topology and location-sensitive form of distributed computing. I believe it is a good definition, but very general. Indeed, it gets harder to define all the different edge use cases we can encounter today. Experience shows that each edge case has its own specificity. Indeed, there are as many edge solutions as customers need, because each business is different and companies have their own ways to differentiate themselves from competitions. It would be an endless webinar if we start describing all the possible situations. So let's figure out 3 situations from which we can successively combine them to support more complex edge use cases. The 3 citations chosen reflect some of the typical resource constraint edge solutions are facing, such as size of the CPU and usually connectivity. The first situation regards a case where at the edge you have plenty of resource in terms of CPU and connectivity or bandwidth. It is relatively a new case that is coming up with the exponential growth of data generated at the edge and the need to execute complex and sometimes mission-critical processes. It is also the most common edge computing case customer may start with due to its low constraints. The second one is more common and is continuing to grow steadily. Gathering and filtering data upfront is becoming an imperative for many companies. CPU are getting smaller for price reason and connectivity, whatever the rise of 5G, and is not everywhere because it's not everywhere or always on. And the last situation regards object with some processing capability, typically intelligent sensors activators that usually are deployed on a large scale. So let's deep into these 3 situations and show how SciSec can help. For each situation, we will present really briefly 4 use cases we are working on with some of our customers. But I will, for the time reason, I will focus only on one specific one and stress the security challenge we encountered on these specific real cases. So this is the first situation. It is typically used to deploy complex CPU-demanding workloads in distributed architectures, such as AI/ML models for the industrial automations, visual recognitions, and so on. So I've put 4 different customer cases covered by this situation we are engaged with. But as I said before, I will focus only on the last one. In the first one, the first examples regard the X-ray control system used in the airport to control the internal of the luggage. The complex artificial intelligence models for analysis has to be obviously protected, because otherwise it will be a major issue when you're traveling with the airplane. The second case is a smart grid case in the energy, for example, in the energy utility sectors, that has to distribute and protect some AI/ML to regulate the grid on the field. Similar case with the manufacturers who wants to digitalize their own know-how for industrial automation purpose. The use case I would like to spend here a bit more is in the retail domain. We are talking about a large retail chain that is looking to deploy their payment operation from the cloud to the edge for performance and operational costs. If this represents an important benefit for the retailer, it is as well creating some operation and security challenges. Starting at the shop. Now, retailers want to protect payment operation process there. They want also to guarantee the data confidentiality of the data payment operations. They want to contain system intrusion into the shop payment system through the infrastructure. And they want also to protect their solution against physical tampering of the servers into the shop. On the, let's say, general operational side, moving from the cloud to the edge, for example, brings obviously more complexities. And here retailers, look for, protections of the communication between the different nodes and the cloud. It's looking for an agile, secure deployment of the payment solution to the shop via the cloud. And constantly has a centralized manage and orchestration of the shop payment solution and the related infrastructures, such as OS update and upgrade. Ideally, it's also looking for an architecture neutrality for these business applications. Here we are talking about payment solutions, but you may have, fidelity cards, customer data, visual surveillance. You want to deploy there without every time recoding this to adapt to the security feature you add. And finally, you want that this solution is scalable and agile to support the evolution of the business, whatever the increase of shops or the decreasing in function of the ongoing activity, the ongoing retail activity. So Mathieu, looking at this challenge we encountered in this retail case, how CySec can help this type of customers to cope with this challenge?
Okay, so in the use case that you described, Luca, we can consider that the payment operations are performed on servers using x86 architecture processing units. The payment system of an organization is distributed between different locations that host one server for payment operations, each of them. So the solution shown on this slide and proposed by CySec for this type of use cases has been described in a previous webinar that we gave with AMD. And the link of this webinar is written at the bottom of this slide and will be shared to the audience through the chat. So to summarize this webinar, in this webinar, we described our capacity to set up a cluster of ARCA nodes in servers running on AMD SEV. So it's SEV, it's a feature from AMD CPUs that provides this confidential computing capacity, and so providing by default data security at rest and in use. So each node of this cluster is connected with the cluster through trusted communication channels. This solution that we call a continuum of confidential computing has been designed to serve distributed architectures of containerized applications. So a Kubernetes orchestration allows a centralized, fast, and resilient container orchestration at scale in this use case. Furthermore, our solution supports all the topology supported by Kubernetes, which make it more or less architecture agnostic, I would say. So now from a security perspective, our system protects against various threats. It protects the data when one or more servers are stolen or tampered with. Of course, the communication of the payment operation are protected within the ARCA cluster, and this is made by default. Confidential computing provides the capability to isolate the containers running in a public cloud from CSP admins and other processes running on the shared processors. On-premise, confidential computing provides a defense against attacks that might be performed on RAM memories of servers, such as, for example, cold boot attacks. This type of security measures might be important when your servers are located in places without a strong physical access control. And then finally, all the security measures provided by ARCA are or can be enforced to limit the possibility of security misconfigurations in your cluster. Okay, so Luca, this is a short summary of our previous webinar presenting a solution for your situation one.
Thanks, Mathieu, for these clarifications. So now looking at the second situation where the abundance of resources is getting less on the edge node with less CPU power. Typically, we are talking here about gateways, small intelligent device who need to gather and protect data from the field and eventually run some processing on site. Again, few examples, such as a railway signaling system that is highly automated to improve performance and efficiency overall. The protection of IoT networks, such as low-power wide array networks that gather a number of sensitive data from the field, like the traffic, the water, or waste management. Single data maybe are not critical, but the sum of it may be very critical if someone can manipulate it. Or the digitalization of the smart grid substation that are usually isolated node running local operations very far from the data center. The case I want to detail for this second situation is around the management of a fleet of drones. Drones are getting a lot of traction in many verticals, such as agriculture, smart infrastructure, geographical observations, emergency management, insurance, and so on. A lot of the information gathered by a drone is sensible and therefore may be under strict control, and this is often requested by the regulator. So drone can generally handle small CPU capabilities, such as ARM-based hardware, due to the weight and the energy consumption limitation that should integrate it within an end-to-end management and security approach. So again, following the same approach, and in the first case, let's look at what happened on the drone side, and in such a fleet, what are the challenges? Obviously, intrusion and taking of control of the drone is a major issue. It's also assuring the confidentiality and the integrity of the data gathered in the drone and stored in the cloud. The physical tampering of the drone, as if someone take it, open it, and can see whatever is inside. The protection, obviously, of the telecom and the telemetry of the control of the drone, the pilot of the drone. And obviously, a situation that is typically when you operate on the field is sometimes you have some discontinuity in terms of connectivities. On the central side, when you have one drone, you can pilot it, but when you have many drones, it's become pretty complex. So you have operational challenge. Obviously, they are very similar to the one that you, Mathieu, described in situation one. But in this case, we are talking about at the edge, small CPUs, typically ARM-based. But you still want to centralize the operation management and pilot it up to the drone. You want to have the assurance that your fleet management update and upgrade up to the drone are properly done, as well as all the functionality, the application you want to deploy to the drone. And obviously, because it's a business that is growing, you want to have the scalability, agility of such architectures to follow the drone fleet expansions. Again, Mathieu, here we are talking about new additional challenge respect to the first situation. Could you explain a little bit how with ARCA Trusted we can adapt to this, let's say, constraint that typically exists in the edge world?
Yes, so Luca, I will start by repeating, let's say, your requirement. So in this drone use case, several end users' requirements have changed compared to situation one. You mentioned the fact that the footprint of the IT device will be smaller than in the previous situation. So for this kind of device, we consider that ARM architecture-based processors are much more frequent. Furthermore, you mentioned that the communication link between the drones and the fleet management system will be or might be discontinuous, making Kubernetes inappropriate. These two requirements make the previous situation inoperable for drone fleet management. So that's why we develop a new solution. So that's the reason why we developed another version of ARCA Trusted OS that is designed for ARM architecture processors. This ARM version of ARCA is also a Linux-based microdistribution designed to run only OCI-compatible containers. Okay. From a security point of view, ARCA on ARM has similar security features than ARCA on x86. This OS is a container-specific OS with a hardware-based chain of trust or secure boot. The kernel and the user space are immutable to prevent modification that might be attempted by malwares in corrupted applications. Furthermore, a full disk encryption is set up by default with the encryption key stored in a TPM. So concerning confidential computing, ARM and AMD provide capabilities that are quite different. So as shown in the figure of this slide, ARM divides its processors in two domains, a secure world or trust zone and an unsecure world, or also called normal world. So the secure world is the trusted execution environment where applications are isolated from all processes executed in the normal world. So ARCA Trusted OS, or our OS, is the host OS of the unsecure world or of the normal world. And the containerized application of the end users, they will be deployed and executed on the top of ARCA Trusted OS, so in the normal world. Nevertheless, ARCA software packages includes the setting up of the secure world with Opti, which is a well-recognized open source project. And so we leverage the isolation capabilities provided by ARM Secure World to protect our crypto API, which is called ARCA Crypto Service. That is, and this crypto service is only accessible to end users' applications through trusted channels. So as you can see on the figure, the cryptographic backend of ARCA, so cryptographic backends, this is the place where all the cryptographic functions are performed. So this backend, cryptographic backend, is deployed in the secure world, so in the trusted execution environment provided by ARM. This means that the cryptographic material and operation used by our crypto API are isolated from all the containers running in the insecure world. So all the features I have just described are the ones of an elementary block, let's say, composed of one board with an ARM processor. Now let's move to the next slide, please, Luca, and have a look at how this elementary block can be connected to a Kubernetes cluster. So as mentioned previously, Kubernetes runtime is not adapted to run on edge gateways because in the far edge, the computational resources are limited and the connectivity towards the core network can be discontinuous. So we have integrated KubeEdge, which is a container runtime that is compatible with Kubernetes and designed and KubeEdge is designed to run with edge gateways constraints. The compatibility of KubeEdge with Kubernetes allows end users to benefit from Kubernetes orchestration features. So especially for large fleet of edge gateways, such as drone, they can be managed in a centralized manner from the cloud or from a data center. This remote management allows simple and fast deployment and updates of the applications running on ARCA. So that's one point. Second aspect that is important is that also the OS, so ARCA OS, running on the edge gateways can also be updated remotely. So in summary, by running ARCA Trusted OS from the cloud to the edge, you get the same set of security measures by default in your entire edge network. Therefore, you own a platform to orchestrate your containers in the edge that provides you a protection of your business data by default while it is at rest, in motion, or in use. On your side, you can focus your energy and time on your businesses. So Luca, this is what I can say about how SciSec solution can address your situation 2. Now let's start with let's present situation 3.
Yeah, here we are introducing external elements to the secured IT infrastructures we presented in situation 1 and 2. But obviously, this external element has to interact securely with it. We have to protect the exchange of the data. This is typically true when we have the interconnection with small sensors, but not only. Think about also robots and so on. So the first case I just listed there, we are working either around the securization of the data flow of the telemetry and telecommand function of satellites. We have some announcements we did early this year. Others will come also on this. Another case is with hospitals that usually have to locate their asset, but they have also to respect the data privacy of their patients. Similar to the hospital case, but on a much larger geographical scale, the monitoring of strategic infrastructure, such as gas pipeline, over dams, highways, and so on, require all the use of large-scale sensors that generate data that has to be protected. The use case I want to deep dive here is in the smart building industry. The adoption of digital control solutions for building offer many advantages in terms of centralizations and agility of the management and control. But if the security is not well managed, someone can get the control of the building and create important damage. Imagine someone opening all the doors or bringing the building temperature to 30 degrees. In nowadays, this would be very painful. So you have to understand that, again, here from the node and centrally, there are additional challenges. At the nodes that are already in the buildings, whatever it is, a gateway or a display, we need to avoid intrusion and control of the gateway and this display, where usually interact and make some actions. We need to assure physical tampering, control the accessibility of the encrypted keys, and obviously, the end user data privacy. Centrally, we need to have the capacity to deploy and manage this light interface for an end user to interact with the building. Assure the management and security continuity with the core infrastructures. It's not two separate words. It must be aligned. Otherwise, we create separation, and there is a pretty risk of infiltration on this side. We need to manage centrally multiple buildings, multiple assets, multiple security key management. So, so a lot of key challenge to manage. And one thing also that is extremely important, we need to let new business functionalities leverage this security. We saw again the need to recode or integrate specific secure elements. So in this case of intelligent device, where it's kind of display, where a typical normal Linux-based OS cannot really run, how can we secure this element? How do we connect them to our secure distributed architectures we describe in situation 1 and 2?
Okay, so in the new scenario that you just described, Luca, the end user wants to securely communicate with devices that are not part of a cluster made of elements running the ARCA Trusted OS. In this case, it is quite common that the application aiming at communicating with external devices uses a crypto API to secure the communication channel. Using what I call a low-level crypto API, such as OpenSSL, is one option, but might be pretty complicated, I would say, if you don't have the proper cryptographic skills in your company. Furthermore, a proper management of keys is mandatory to implement a secure channel. Again, key management systems require expertise in cryptography that might not be part of your company. So ARCA Trusted OS embeds a crypto API that includes the functionality of a crypto service, a high-level one, and the ones of a key management system. ARCA Crypto Service is a high-level crypto service designed to reduce the complexity of use of crypto APIs, of crypto functions. ARCA Key Management System is also designed to simplify the management of keys and allows key management at scale with distributed vault within the whole ARCA cluster. So this means that secure key storages are securely interconnected within your whole ARCA cluster. This provides you the capabilities to securely share crypto resources within your cluster. This crypto API can rely on certified hardware-based secure modules, such as HSMs, so hardware security modules, or TPM, trusted platform modules. In this case, your keys are in clear only when they are located in one of those secure modules. In terms of families of cryptographic functions proposed by ARCA Crypto API, you can access the most commonly used crypto functions to secure communications, of course, but also to perform some business functions in the area of blockchain. And then finally, let's say the particularity of ARCA Crypto API running on ARM is that when you use our fully software-based solution, the cryptographic backend, this is again the only place where the keys are in clear. So this crypto backend is located in the trust zone or in the secure world provided by ARM. This means that this crypto backend is cryptographically isolated from the containers running in the secure world. This brings a high level of security on the keys, protecting your business. Okay, so Luca, I have covered all the aspects offered by our solution to help in situation 3.
Thank you very much, Mathieu, for your explanation and CySec offering and capabilities. We've seen different edge situations and how CySec can handle the IT infrastructure management and security challenges. How does it like to bring them all together to be closer to real cases? Let me try to summarize Mathieu's speech. But obviously, Mathieu, please help me if I do say stupid things. Edge computing solutions are distributed, heterogeneous, and face multiple resource constraints. To manage such complexity, there is no one-fit-all solution. To overcome this challenge, CySec provides IT infrastructure solutions via its adaptable micro-distribution Linux-based operating system, ARCA Trusted OS, that homogenize the level of security along the architectures, and in particular, it mitigates those challenges meanwhile keeping the container agility of modern IT architectures, small footprint, Kubernetes versus Kubernetes, and so on. and a common hard-based security approach. It simplifies the operation via centralized management capability leveraging Kubernetes, so keeping the IT agility further down to the edge. It protects your data via the security enforcement along the architectures within the clusters and their dependencies, including the technology behind confidential computing, immutable execution environment, secure boot, crypto services, enforcement of trusted communication, channel between pods, API, our API for key management systems. And finally, it makes transparent for the business activity. So there's no code, there's no need to record an applications, and a business can just leverage the benefit of containers, thanks to the creation of a kind of abstraction layers within the IT infrastructure up to the edge and the applications.
Okay, I think Luca, you made a great job, and I don't need to add anything.
Thanks, Mathieu. So we are going close to our the end of this webinar. Let me just summarize, or let's say provide you the call to actions. So if you need to protect sensitive data or mission critical processes at the different edge layers, ARCA Trusted OS can help you by delivering a secure container-based IT infrastructure from the core to the edge, including smaller footprint such as ARM-based gateway. Do not hesitate to contact us for major information. It is important to include the security, and one thing that is very important is really to include the security aspect upfront in the design of the solutions, and not thinking afterwards. This may painful and very costly solutions. So, and finally, if you want more information, just visit SciSec, ping us. We'll be more than happy to follow up with you. You can find obviously more information on the use case and deep dive in some video in blogs we have on our website. So let's stop sharing my screen and let's move to the Q&A sessions. Okay, here we are. So we exist. So we are just for the attendance, and let me check if we have some questions. Okay, so here we are. We have one question that Vanda is asking. Do you have already certified ARM-based or qualified ARM-based boards with running on ARCA Trusted OS? What we can answer here?
So that's, I need to answer it.
Okay.
Or I take this one. So that's a very good question indeed. With ARM technology, with boards hosting ARM processing unit, it is quite frequent that there are some specificity from one board to, from one board family to another one, especially for the secure boot, and that's one element that we exploit in our solution. So this means that qualification is not as straightforward as for x86, for example, architecture of CPUs. So presently, we have developed our solution on a board from ST Microelectronics. So we have qualified one family of boards from ST Microelectronics. We are working on a Raspberry Pi 4 board to qualify our ARCA Trusted OS on this type of board. And we consider also starting investigation on a board from NXP. But it's not clear now which family will be.
But generally speaking, it's also highly driven by the use case you have, and obviously we can focus on different board. ARM-based board are very peculiar; they have to be adapted to the different situations, and obviously we are also keen to work in this different case. Then there is another question from Giacomo. Giacomo is asking. You present the drone case. What happened if the drone is stolen? How we must be sure that everything is controlled? Sorry, I have my glasses. I have some hard time.
Okay.
Maybe you can answer here. Yeah.
Yes. So when you say control, I guess it's okay. It's about the security of the data. So in this case, again, we by default we have a full disk encryption of the data with a key that is stored in a TPM. And to release the key that is stored in the TPM, so to start to decrypt the hard disk or the persistent memory, we need to, I mean, the system needs to be able to boot. So there is the secure boot step. And if there is no successful secure boot, then there is no release of the key stored in the TPM and no decryption of the persistence memory. So this means that if an attacker does not have any privilege on ARCA Trusted OS, so for example, the root access with the password, this attacker cannot access to the data that are encrypted again in the persistent memory.
Thanks, Mathieu. Okay, we are running out of time, so let's take other two questions. One is from Tao, is asking how is possible to test ARCA Trusted OS. Well, I can take this one. I mean, typically, you know, we have NFR, so I think let's start in contact, and we are more than happy, you know, to let you use it in a different context, maybe starting in a cloud like Google, where you can experiment, and obviously afterwards in a different situation on premise or eventually at the edge on typically ARM-based solutions. But again, as Mathieu mentions, this is something that have to be adapted in function of the type of board you are working on. Final questions. Let's ask Barbara, who is asking, are you also thinking of adding monitoring capabilities within ARCA for constantly checking the integrity of containers running on ARCA?
Okay, so I will take this one. Okay, so presently we are focusing on, let's say, protecting the infrastructure, the OS, and the runtime, the container runtime. But we are currently evaluating the possibility to integrate an IP from a partner that will allow to monitor, let's say, strange behavior or let's say unexpected behavior in application, in containers running on ARCA Trusted OS. This monitoring system is hosted in the trusted zone, so running on ARM again. So we will use this trust zone to keep, let's say, secure the monitoring system that will monitor the behavior of application. And with this kind of system, we expect to be able to detect some attacks, some corruption of application that run on ARCA Trusted OS. But for the moment, it's just under investigation. It's part of our roadmap. Maybe we will have some first development version in end of 2023 or 2024, something like this.
Excellent. So now we see we are, as if fundamentally, running out of time. For any other person in the audience who wants to have, you know, further questions, you are kindly invited to share. I mean, send us some questions. You will receive anyway some email to recap this webinar, and then answering directly to us or asking directly to us some questions. So it's time to close. So I would like to thank all the people who joined this event and take the time to listen to us. We look forward to having you in our next webinars. This time we will be more focused on real case with some of our customer and partners on presenting some concrete case. So stay tuned for what will come in the next coming months. Thanks everyone for your participations, and for the one who are on our time zone, have a nice lunch. Thank you very much. Bye-bye.
Thank you. Bye-bye.